This is the 8th lecture on Lagrangian mechanics. In the earlier class, in the earlier lecture, we have derived the Euler-Lagrange equation for non-holonomic system. Holonomic system for which the equation of constant can be written in the form of Fabian, but is not integrable. Then we found that the equation of motion is I is equal to 1 to k number of constant lambda I AIM, where AIM are obtained from the equation of constant. The equation of constant is written as m is equal to 1 to n AIM dqm plus bi dt is equal to 0. This is the equation of constant, and AI are the coefficient, AIM are the coefficient of dqm in the equation of constant. And we also identified this is as the force of constant related to the electric way of freedom. We applied the theory to few problem to be specifically applied this theory to a simple pendulum, and then we also applied the theory to cylinder rolling down an inclined plane, and we remarked that the theory can be applied to a sphere rolling down an inclined plane or a hoop rolling down an inclined plane just by changing the value of radius of gyration. Today we consider a particle as the next example. A particle on the outer surface, on the smooth outer surface of a sphere, outer surface of a sphere of radius a. So this is the problem. So we have a particle of mass m which is moving on the outer surface of a sphere. So this is a sphere of radius a. It is a sphere of radius a. If we consider the origin of the coordinate system to lie over at the center of the sphere, so the equation is x square plus y square plus z square is equal to a square. If we write it in the form of Fabian, this becomes x dx plus y dy plus z dz is equal to 0, so that ax is equal to x, ay is equal to y, and az is equal to z. So these are the quantities A. And we consider the coordinate system in such a way that xy plane is the horizontal plane. So xy plane is the horizontal plane and z axis is the vertical axis. Furthermore, we said that V potential energy is 0 and z is equal to 0. So the Lagrangian of the system is half m x dot square plus y dot square plus z dot square minus the potential energy is mzz. So if we apply the Euler-Lagrange equation to x direction of freedom, then we get del L del x is equal to 0, del L del x dot is equal to mx dot, so that ddt of del L del x dot minus del L del x is equal to ax lambda gives us mx double dot is equal to x lambda. This is equation 1. Similarly, the y equation gives us my double dot is equal to y lambda. This is equation 2. The z equation is slightly different because of the presence of this. So we get mz double dot plus mg is equal to z lambda. This is equation 3. Now we multiply equation 1 by x, 2 by y, 3 by z. So what we do, 1 into x plus 2 into y plus 3 into z. So we get on the left hand side x double dot plus y double dot plus z double dot plus gz is equal to x square plus y square plus z square times lambda. So this is a square. This is simply a square. And what is this? If we consider this equation of constant, if we and differentiate it with respect to time, then we get x dot plus y dot plus z dot is equal to 0. If we differentiate it once more, we get x double dot plus y double dot plus z double dot is equal to minus x dot square, y dot square, z dot square. So this is simply minus v square, but v is the velocity. So this term will mgz minus v square is equal to a square lambda. Or we can find lambda is equal to so this is lambda is the force of constant. This is the force of constant. The particle of mass m remains attached to the outer surface of the sphere so long lambda is greater than 0. So the mass remains attached to the outer surface. We assume the surface to be frictionless so long as lambda is greater than or equal to 0. When lambda is 0, it just starts slipping. So the condition for adherence, the condition of adherence is gz must be equal to this greater than v square, and for the critical value is gz is equal to v square. This is the critical value. So for other case, this is the situation when the body just on the verge of slipping off the spherical surface. And for if this is gz is less than v square, then it flies off the spherical surface. This situation can also be treated in a way which gives us much more information. So the same problem, we are again solving the same problem. This time we shall use spherical polar coordinate system. So we use a spherical polar coordinate system for which the equation of constant simply reduces to r is equal to a, and if we consider the motion of the particle in a vertical plane under the action of gravity, then we may choose that the particle is constrained to move in xz plane, where z-axis is the vertical axis and the particle is constrained in a vertical plane. When the particle is confined in a vertical plane, we take SZ plane. We have phi is equal to 0, phi of spherical polar coordinate system, phi. So we use the spherical polar coordinate system r theta phi with phi is equal to 0. This is the simplification. This condition was not imposed in the earlier calculation. This is an extra condition we are imposing. In fact, we are considering the particle moving down the smooth surface of a circular ring or circular hoop, whose axis is horizontal one. So the plane of the hoop is confined in xz plane. So the Lagrangian L for the system is half m r dot square plus r square theta dot square plus r square sine square theta phi dot square minus m g z. For z we write r cos theta. As for our choice, this part is not there. So because we have considered the particle to remain in phi is equal to 0 plane, so the Lagrangian simplifies to half m r dot square r square theta dot square minus mg r cos theta. So, and the equation of constant is dr is equal to 0, which gives ar is equal to 1, a theta is equal to 0 is equal to a phi. So this is the restriction. Now coming to the equation del L del R. Del L del R is m r theta dot square. And del L del R, sorry, there is another contribution to del L del R. So this is minus mg cos theta, and del L del R dot m r dot. So the equation that we are going to apply is del AR lambda. So this we get now the condition of constraint is that L is equal R is equal to constant. So it also gives you that R dot is equal to 0 is equal to R double dot. So that we get ma theta dot square plus mg cos theta is equal to lambda. This is one equation. This is the outcome from our equation, the theta equation. Del L del theta, this is being L, this is del L del theta is equal to mgr sine theta with a plus sign, and del L del theta dot is equal to mr square theta dot. So the Euler-Lagrange equation for theta degree of freedom is del L del theta dot minus del L del theta is equal to a theta lambda. A theta being 0, a theta being 0, we get ddt of mr square theta dot is equal to 0. This gives you, since r is equal to a, so m s square theta double dot is equal to 0. Sorry, this equation has been written wrongly. This is the del L del theta minus mgr sine theta is equal to 0. Since r is equal to a is constant, we get ma theta dot is equal to ma theta dot is equal to g sine theta. So m is also cancels out. So this is theta double dot is g sine theta by a. This is the equation that we get for theta double dot. We see from equation 1 that the lambda, undetermined multiplier lambda depends on theta. To get the theta dependence of lambda, we differentiate this equation with respect to theta. So by operating dd theta, we get minus twice ma theta dot, theta double dot, this is the differentiation of this term, minus mg sine theta, theta dot, then this is d lambda we have performed ddt. So this is d lambda d theta dot. Theta dot is present in all the terms, so we draw theta dot from all these three terms. So what we get, minus 2ma theta double dot minus mg sine theta is equal to d lambda d theta. If we put the value of theta dot from this equation, so a theta dot is equal to g sine theta, so this becomes minus 3 mg sine theta. So using equation 2. So we integrate it. On integrating, we get lambda as a function of theta is equal to minus plus 3mg cos theta plus a constant of integration c. To evaluate the constant of integration, we said that when theta is 0, that is when the particle is on the top of the sphere, the force of constant is simply mg. So we set at theta is equal to 0, lambda is equal to mg, which gives c is equal to minus twice mg. So this equation becomes mg taken common, 3 cos theta minus 2. Again, the particle remains attached to the sphere so long as this is greater than 0. So the critical condition is, let me write here, critical condition. For attachment, so for attachment, to the sphere, lambda must be greater than 0, so that cos theta must be greater than 3 by 2. For detachment, lambda is negative and cos theta must be less than 3 by 2. Critical value or critical case, lambda is equal to 0 when the particle just on the verge of slipping off the or getting detached of the surface of the sphere. We have cos theta c is equal to 2 by 3. I have made a mistake. This is 2 by 3 because it is not possible to have value of cos greater than 1. So this is 2 by 3, which gives theta c is equal to around 48.2 degree. So if the angle theta, theta is greater than 48.2 degree, the particle remains attached to it, and if less than this, it slips off the surface, spherical surface. So this is an interesting problem that could be solved solved in terms of Euler-Lagrange equation for non-holonomic system. As I have pointed out earlier, that's the calculation that we have presented in the second case, that is when using r theta phi coordinate system and by freezing the phi equation is actually the calculation when a mass m slides down a ring placed in a ring whose plane is lies in a fixed horizontal plane. Now we just mentioned few cases for the example. A particle is moving on the inner surface of a paraboloidal of revolution. So we consider a particle on the surface of a paraboloidal. The paraboloidal of revolution is like this. And the equation is x square plus y square is equal to az. If we switch over to cylindrical coordinate system, it is rho square is equal to az, or to rho d rho minus a dz is equal to 0. so that A rho is equal to 2 rho, A phi is 0 and AZ is equal to minus A. These are the quantities A required there. And the particle is moving on the outer side, on the inner surface of this paraboloidal of revolution. So the Lagrangian is half m rho dot square plus rho square phi dot square plus z dot square. If we consider V is equal to Z is equal to 0 at the 0 level of potential, then the potential is mgz. So the rho component, del L del rho is m rho phi dot square and del L del rho dot is equal to m phi rho dot. So that the corresponding equation ddt of del L del rho dot minus del L del rho is equal to A rho times lambda gives us ddt of m rho phi dot square minus del L del rho dot is this, so ddt of m rho dot minus m rho phi dot square is equal to twice rho lambda. This is rho equation. And coming to phi equation, del L del phi, since the L Lagrangian doesn't have any phi dependence, it is 0, and del L del phi dot, del L del phi dot is m rho square phi dot. So the equation is ddt of you see that this is 0, this is 0, so what we get ddt of m rho square phi dot square, not phi dot square, this phi dot is equal to 0, that gives m rho square phi dot is equal to some constant, L is equal to some constant. And del L del Z is minus mg, minus mg is okay, and del L del Z dot is equal to mz dot. So the equation ddt of del L del Z dot minus del L del Z is equal to Az lambda gives us mz double dot plus mg is equal to minus a lambda. These are the three equations. This one, this is 2, and this is 3. These are the equation of constants. We can put them suitably on the equation of constant to get further information. There are other examples also cited in the problems given to you. I am just mentioning one more type of problem. A particle a particle rolling down or a particle descending down an inclined plane. This type of problem. So particle on an inclined plane. This is a type of example that we shall consider for this non-holonomic system. So for further example, particle on an inclined plane. So we have an inclined plane like this. So we choose our coordinate system. This is as x coordinate system, this is y coordinate system, and this angle is alpha. So the particle coordinate is, particle M is over here having coordinate xy, and this x is equal to 0 level is also chosen as the 0 level of gravitational potential. So the equation of constant is that y is equal to tan alpha times x. Since this is constant, we say this is Cx, where C is the slope of the inclined plane. So we have dy minus C dx or minus C dx minus dy is equal to 0. So Ax is equal to C and Ay is equal to minus 1. And the kinetic energy, the Lagrangian is half mx dot square plus y dot square. This is the kinetic energy part, and the potential energy is minus mgy. So if we solve for L equation, so del L del x, del L del x is equal to 0, and del L del x dot is equal to mx dot. So ddt of del L del x dot minus del L del x is equal to ax lambda, gives us mx double dot. This is 0 and this is c lambda. This is equation 1. And for y equation, del L del y is minus mg, and del L del y dot is equal to my dot. So ddt of del L del y dot minus del L del y is equal to ay lambda, gives us my double dot plus mg is equal to ay is minus 1, so it is minus lambda. This is equation 1, this is equation 2. Now we can write the equation of constant. Further we can write the equation of constant as is y is equal to cx. If we differentiate it twice with respect to time, we get y double dot is equal to cx double dot. We get the expression for y double dot from here. It is minus lambda minus mg, and on the other hand x double dot is c square lambda, or c square plus 1 lambda is equal to minus mg, or the force of constant is minus mg 1 plus c square. So this is the force of constant. One one more thing may happen, that same problem, but in this case we have attached a spring along x-axis. That is to say, there is a spring and the particle is attached by a massless rigid rod, so that along x direction there is a harmonic oscillation, in which case the Lagrangian changes by a term minus kx square, and the equation will change accordingly. And finally, this equation, this lambda equation, in this case lambda equation changes to lambda is equal to ckx minus mg divided by 1 plus c square. I am just giving another problem for you to work out on yourself. This is the particle moving on a elliptic paraboloid. A particle on the inner surface, particle on the inner surface, which is a smooth one, of a elliptic paraboloid, or of an elliptic paraboloid. The paraboloid, the equation of the elliptic paraboloid is given by ax square plus by is equal to cz. So, in the last two lectures, we have discussed the Lagrange's equation as applicable to non-holonomic system quite extensively. We have developed the theory and worked out a good number of problems. From the next class onwards, we shall discuss few special Lagrangian, that is Lagrangian for charged particle in electromagnetic field, and such problems will be taken up from next class onwards.